Good morning, chemists. I'm continuing our conversation on biomolecules, aka macronutrients, just getting the chemistry behind some of the content that we're talking about in our nutrition class. So last time we were together, we were looking at a couple of vocabulary words. We looked at hydrocarbons and heteroatoms. We looked at saturated and unsaturated. We will continue this conversation a little bit more. Basically, we looked at how we can code this information with formulas, with a structure, and then with a sort of cryptic method, and just being able to interpret that. And again, we'll practice some of that later on. So just continuing with vocabulary, we're going to talk about, there are lots of functional groups, and we are going to focus on three, maybe four. I already gave you the name of one. We called this group, the last video, CH3, a methyl group. And so it's interesting and important when we start talking about some of the names, omega-3s and 6s. When we start talking about fatty acids, we'll refer to the methyl group. When we refer to proteins, one of the important groups is an amine group. It's an NH2 group where you have this nitrogen and two hydrogens attached to it. That's going to be really, really important when we, again, speak of proteins. Carboxylic acid, this is one of the ends of a fatty acid, which we'll speak about. COOH is the functional group. The configuration is really specific. It's got a double bonded oxygen and then an OH group. That would be really important. Also known as our carboxyl group. And then the alcohol group, just an OH, pretty basic, also known as hydroxyl group. So that vocabulary is there. Just making sure as you think through the process here, this group right here is, it looks the same, but when you look at the configuration as a whole, you don't want to just misinterpret. So making sure when you see the carboxyl group, you're seeing the COOH, the double bonded oxygen, and the OH group makes it unique and different. Okay. Just some vocabulary, not a big deal on this one, but an alkane basically is a molecule that has single bonds in it. And for our purposes, right, this is going to be what we're going to call saturated. Okay, an alkene, not a big deal, but just know that there's all kinds of chemistry nomenclature in organic chemistry. This implies that there's a double bond. And for our purposes, that's going to be an unsaturated molecule, meaning it can hold more hydrogens than it should. An alkyne, we're probably never going to see this, but an alkyne is a triple bond, and I'll just put it in there because it makes it nice and clear, right? So an alkane is a single bond. It's 2 electrons being shared. An alkene is a double bond. It's 4 electrons being shared. An alkyne is a triple bond. It's 6 electrons being shared, right? Okay, so we have spoken about polarity. I can't tell you how important it is. It keeps showing up and up and up. And so we've talked about it in the context of electronegativity, right? Electronegativity. So this measure of the attraction atoms have for each other. When we talk about polarity, we can talk about the polarity of bonds, right? And so when we look at the difference in the electronegativity of greater than or equal to 0.5 versus electronegativity of less than 0.5, right? Less than 0.5, we call this a polar bond, and we call this a non-polar bond, right? When we ramp that up into the geometry, so when we start talking about how the bonds manifest in the shape, right, around the central atom, basically, that's where that all goes. Wow. Okay, that was crazy. So let me go there again. So essentially, when we start talking about this, the implication of this is hydrophobic and hydrophilic. So the words themselves help you understand what they mean. So a hydrophobic particle, and we can have a particle a polar molecule, or we can have the end of a large molecule or a part of a large molecule that's hydrophobic. The word itself, hydrophobic, means water-fearing, right? And what that means, this can be a molecule, or it can be a part of a molecule, part of a large molecule. And basically, this molecule itself is going to be nonpolar, because nonpolar substances don't like polar water. Okay. Hydrophilic, you can see, is water loving. Okay. And so this, again, can be the same. It can be a molecule itself, or a part of a large molecule. There can be a part of it that's hydrophilic. And the implication of this is a polar molecule. So this molecule is polar, and the reason it matters, this sort of verbiage of hydrophobic and hydrophilic, is we're talking about water, and H2O is polar, okay? And that's a big, big deal. It dissolves things that are polar. It doesn't dissolve things that are nonpolar. And the chemistry of that polarity is really huge and important to a lot of things. Okay, so when we start talking about the macronutrients or biomolecules, however you want to call them, as you know, there are 3 versions of macronutrients. There's fats, proteins, and carbohydrates. When we look at a fat, it's the most complex of the particles, and as you know, it is the one that gives us the most energy. So I'm going to give myself a lot of room to draw on this so that I can get this in here. So basically what we want to do is we want to talk about fats, and for the most part, there's more to this, and we'll talk about that in a PowerPoint, because I can't draw these as well, but I want to talk about triglycerides, and you may have heard that word before. There's sort of an interpretation, right? There's tri, right? And then there's the glyceride part. And so basically the word 3 it shows up, or the number 3, and then glycerol is the sort of implication. So basically the 3-glycerol, so the 3 refers to 3 fatty acids that are attached to a glycerol, okay? And I like to call it a glycerol backbone. Okay, I'm going to try to draw this. I'm not going to do the greatest job. I will show this to you in a PowerPoint in class, but basically I want us to see what this looks like. So the 3-carbon backbone is a glycerol. It's got 3 alcohol groups. You can see it gets messy right away. Okay, 3 alcohol groups. So the alcohol groups are what make this glycerol. The all talks about alcohol. Okay, attached to that in a fatty acid is 3 fatty acids, and fatty acids are basically a carboxylic acid end, and then they are a long chain of carbons. I'm just going to draw them in here, and then there's a methyl group on the end. And generally speaking, these chains, when we're talking about triglycerides, are 16 to 18 carbons long, so they're very, very long. And often you'll see them written like this. You'll see them written with a chain like this. And, well, let me try it again. They'll have, and for our purposes, when you guys make these, an R group, meaning there's a long chain of carbons behind it. Long chain of carbons. Okay, so when we start putting these together, into our triglyceride, what I want you to notice is, just as we've spoken before, there's this condensation reaction that happens over and over again. So it turns out that this OH and that hydrogen right there will drop off and make 3 water molecules. Okay, and then the glycerol is attached to those fatty acids, and that's what makes a triglyceride. Okay, so I'm going to try to draw that, and I'll see how I do. So I'm going to draw my my backbone, if you will. Okay, and then this is going to be the long chain from the first one. There'll be a COH long chain from the second one, and then long chain from the third one. Okay, and so this attachment right here is what happened right here. So we get a triglyceride. That's the game. Okay, so when we talk about a fatty acid, so I'm just going to talk about a fatty acid really fast. I'm going to draw that on here. So I have a methyl group on this end, big chain of carbons, and I have my COOH group. What turns out is this end of this molecule is polar. This is the hydrophilic end. Okay, so this is polar. So we said that there are parts of a molecule that are polar, and that's because of the bonds that exist. So this carbon-oxygen bond, that carbon-oxygen bond, and that oxygen-hydrogen bond, there's polarity there, and so that makes this a polar part of this molecule. It turns out that when we think about the rest of the molecule, all of these carbon-hydrogen bonds are all nonpolar. So these are nonpolar bonds. And that means that this whole part of this molecule down here is nonpolar. And so essentially we get this, we can have polar parts. And so we call this the hydrophobic end. And that end is not going to like water. It's going to actually stick itself out of the water if it's in there. And that's one of the reasons why fats don't dissolve in water very well. Okay. There's more that we want to talk about with fats, and so I'm going to add myself one more page so I can draw all over it. I want to talk about cis and trans. Okay, so this is the orientation of hydrogens. Orientation of hydrogens around a double bond. That's basically what it comes down to. So first and foremost, when we talk about cis and trans fats, and we're going to use that word, okay? Basically, this is the orientation that the hydrogens have. So when we look at our fatty acid, okay, so I'm going to draw that in there. I'm drawing a double bond. That right there makes this an unsaturated fatty acid, unsaturated. And I have a better picture of this on our PowerPoint. Unsaturated fatty acid. Right, these are the good fats we want you to eat, right? And if you understand that each of these have a hydrogen on there, what I want you to see is in this case, this is not a good unsaturated fat because this is a trans fat. So how do I know it's a trans fat? When I look at the hydrogens, they are opposite each other on the double bond. So here's my double bond. And these guys are oriented above and below, if you will. So this, we're going to call this a trans. We're going to call this a trans fat, or the orientation of the bond is a trans double bond. So if I were to draw a good fat, a good unsaturated fat, this is hard to do, so I'm trying. Basically, I'm going to put my double bond in there, and I'm going to go this way with the rest of my molecule. So what I do is I put hydrogens on the same side. Okay, so I'm going to go back to this color. So basically, there's our double bond, and there's our two hydrogens. So where these two are on opposite sides, these are on opposite sides of the double bond, opposite sides of the double bond. Right? These guys are on the same side of the double bond. Okay, this is cis, this is the cis orientation, and this is the trans. So when we talk about trans fats, that's what we're implying. We're talking about hydrogenated fats. The food industry basically hydrogenates food so that it'll last longer on the shelf. And so basically, that's kind of what's going on. So this trans fat's in the body, it doesn't know what to do with it, digest it as if it were a saturated fat. Okay. I will go over that again in the PowerPoint. Just want to get that in your notes. So when we think about fats, right, I've got the cis and trans there. We're talking about lipids for the most part, the triglycerides, and like I said, there are more to them. There are sterols, and cholesterol. And we can talk about those in class a little bit more when Carrie and I are together. Okay. You are probably a little bit more familiar with the carbohydrate, right? So we talk about monosaccharides, right? And we know there are 3 of them. The most important one is glucose, right? So glucose is our most important monosaccharide, and you guys are making those in your lab. And so, the orientation of the carbons, we know it's C6. I have so much trouble with that. C6H12O6, right? And we have 5 carbons in the ring. Let me try that again. I'm not doing that very well. So we have the oxygen with 5 carbons, 2, 3, 4, 5. And then we have a carbon outside the ring, CH2OH up here. And then we talked in class about the orientation of the OH group. So the hydrogen on top, so it's down, down, up, down, as far as our orientation of our OH groups, right? So if we think about this part being the ring of the carbons, right? The first 2 alcohols are down. The third alcohol, if you count those carbons from the oxygen, 1, 2, 3, 4, 5 in the ring. That orientation of the OH groups is really important. And this carbon is up, and so there is a hydrogen down here. So when we count up our carbons, we get 1, 2, 3, 4, 5, 6, right? We get our oxygens 1, 2, 3, 4, 5, 6, and then our hydrogens. I hope I counted those right. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that works. Okay, so that's our basic unit. And what we're talking about is when we put these together to make a disaccharide, you guys are doing this in your lab. The next monosaccharide, I'm not going to try to draw that now, here is going to join right there, right? And how those join together depends on how we're able to digest them. And we could talk about that in class as well. Okay, so we'll talk more about this. I just want this to kind of be in your notes. You guys are working on these in lab, and so this is going to feel a lot better once you do that. Last macronutrient, proteins, right? The general structure of a protein, it's made of amino acids, and we'll talk about those in class. Some are essential, meaning we have to eat them, and some are non-essential, meaning if we eat the right materials, we can make them. But the general structure, we've got a central carbon and an R group. So this is what makes them all different. We've got our carboxylic acid side, our amine side, and then a hydrogen here. So that's why we spoke about these functional groups, right? There's the carboxylic acid side, there's the amine, and then this is right here, which makes each of them different. They chain together right here with this nitrogen, the amine side. So the amino acids will chain together to make proteins. And guess how they do that? Well, they do it by a condensation reaction, right? The OH right here goes with this hydrogen, and then we make a bond right here, and often you'll hear it called a peptide bond. So when we eat proteins, we break these down. We break the peptide bonds, and we have to put water back on. When we make proteins in our body, we have to, we drop off the water. So again, that water drops off, right? And again, that's a condensation reaction. I didn't mention it up here, but when monosaccharides connect to another monosaccharide, make a disaccharide, or they chain together in these long chains of glycogen and starch, basically every time the water drops off. So every time these particles put themselves together into something larger, water drops off, that's condensation. And every time we digest them, we put water back on the molecules so that the hydration reaction occurs. Okay, I think I'm going to call that. I'm going to go back and do the problems here so that you guys can see what I want you to do with this. I'll give you these answers and then I can upload this to Canvas. Thanks so much for listening. Hope you're having a great day.